let's do a few problems that illustrate using the fundamental theorem of arithmetic. The first three have a lot to do with the investigation we did a while ago before we knew as much about divisibility and the structure of numbers. And so this will give a lot of hints as to how we could go back and find some patterns or even formulas for the first few problems on that investigation back from Module 3. So how many divisors does 19 to the 8th have? Well, 19 is prime, and so there's this. We know that anything dividing that number has to be just a smaller power of that prime. That was one of the ones in a previous video. So certainly 1 and 19 squared and 19 cubed, and then all the way up to 19 to the 8. So this is including itself and 1, just to be specific. I think I said that in the later one, but I forgot to do that up here. Okay, so how many is that? Well, that's really 19 to the 0 and 19 to the 1 up through 19 to the 8. So there's really just going to be 9 divisors. So when it's a prime, everybody observed that it was very simple. It's just 2. But when it's a power of a prime, it's really quite simple as well. It's just that power plus 1. Okay, oops, that's an 8 plus 1. Okay, so that's a nice little warm-up. What about how many divisors does something that's not just a power of a prime have? Well, we could start kind of just listing them out. 1 works, 11 works, 13 works, 11 squared works. Well, and then 11 like cubed times 13 squared, that seems a little random. But the previous problem gives us a big hint in terms of how to think about this. The key is that it has to be a power of 11 times a power of 13. Okay. And it can't be, the power of 11 has to be between 0 and 5, and the power of 13 has to be between 0 and 3. So really there's two choices. What is the exponent on 11? What is the exponent on 13? Aha, okay. So in other words, it's going to be something of the form 11 to the A, 13 to the B, and we can choose A to be anything from 0 to 5, that's 6 choices, and B can be anything from 0 to 3, that's 4 choices. You could even make a little grid of it if you want. Let's see. You could make a grid, I won't make the whole thing, but you could do like a 4 by 6 table. You could have 11 to the 0 times 13 to the 0, and then 11 to the 1, 13 to the 0, 11 to the 2, 13 to the 0, and so on, up to 11 to the 5th, 13 to the 0. Those are all different numbers. They have different prime factorizations. And then 11 to the 1, 13 to the 0. 11 to the 1, 11 to the 0, 13 to the 1. My bad. 11 to the 1, 13 to the 1, etc. And then like down here, it'd be 11 to the 0, 13 to the 3. And here, we'd get all the way up to the number itself, 11 to the 5, 13 to the 3. Okay, so you have a grid where it's 4 by 6 grid, so there's 24 total different factors. So we can see that that kind of question of counting the number of divisors becomes much easier when you think about it from the point of view of the fundamental theorem of arithmetic. So we can go backwards. We can say, well, let's find some numbers that have exactly 6 positive divisors. And it doesn't say find all of them, okay? Well, so what's one way that could happen? It could be analogous to 19 to the 8. It could be just a power of a prime. And if that power, if n is p to the 5th, then that works. Okay, so for example, 7 to the 5th, you get 1, 7, 7 squared, 7 cubed, 7 to the 4th, and 7 to the 5th. Okay, so any prime to the 5th power is going to work. So that would answer the question theoretically, but It's kind of nice to see if there's any others. Okay, well, it might be something more like this. Here we got 5 plus 1, 6, times 3 plus 1, 4. And here, let's see, 6, well, 6, it factors. So it's interesting, we're actually factoring the target number instead of the actual number that we're going to find the number of divisors of. So 6 equals 2 times 3. So I claim a prime to the 1 power and times a different prime to the 2 power works as well. So for example, n equals 3 times 25 equals 75. I claim that has exactly 6 factors, 6 divisors. And again, that's including 1 in itself. So that's a little bit of a more complicated version where we're trying to go backwards, but that shows if we can do this kind of problem, it shows we're really getting a pretty good handle on this number of divisors problem that we approached quite a while ago. Okay, there's just one more I have, and make the video a little longer, but I'll just put it in here. So this is from the book. And we have 3 natural numbers, a, b, and c, with the GCD of a and b being 30, of b and c being 24, and a and c being 84. Why not? Let's just find some numbers, some triples like that. But if we think about factoring, think about prime factorizations and FTA, we're going to be able to see that that's not really possible. Okay, because let's look at the middle one, for example. Let's look, well, let's see, which one should we start with? Yeah, let's look at the middle one. We know that 24 divides B and C, so 8 certainly divides B. Okay, so 8 divides B. Okay, and let's look at the third one. Notice 4, that's a divisor of 84, and so that divides A. Okay, so what, right? No contradiction seemingly right now, but let's look at the first statement now. The GCD of A and B is supposed to be 30. Well, that only has 1 power of 2 in it. Okay. So in particular, 4 does not divide A or B. And excuse me. So 4 does not divide. Oh yeah. So let's see. Oh yeah. So let me get the consequence first. From the last two, if 8 divides B and 4 divides A, then it seems to be that 4 is going to divide A and B. But wait a minute. If I know the GCD of A and B is only 30, that only has a factor of 2 in it, does not have a factor of 4, 4 cannot divide A. And so we have a contradiction. So what do we use there? We focused on a prime and prime powers and tried to see what all these statements say about basically how many powers of 2 fit into A and B, how many powers of 2 fit into B and C, how many powers of 2 fit into A and C. The factor of 3 here was kind of irrelevant. The factor of 5 here was kind of irrelevant. The factor of 7 here. We might have been able to play with those. But the thing that was in common was exactly how many factors of 2 go in. And it was just incompatible. That this is saying that B and C and A all have a bunch of factors of 2 that go in particular 2, so a factor of 4. And that's a contradiction with this guy, which is putting an upper bound on how many powers of 2 go in. So lots of good stuff with FTA.